is advanced conduction series. So the background has been changed. So I am currently in my hostel room in IIT Kharagpur, and it is a very hot summer here. Okay, so I mean, I may have to turn on this stand fan that is in my room, okay, and that may create some noise, because of which I apologize to all of you beforehand, and that will be the issue if I have to turn the on. I mean, I have to turn the fan on. Otherwise, it will be fine. Okay. So now let us directly jump into our advanced conduction series. So in the previous lecture, I gave you some homework. The main homework was to express this Q dot G, the heat generation rate, the total heat generation rate in terms of the volumetric heat generation rate. Along with that, I also gave you some basic conceptual questions. There was a good interview question, right? And also some basic conceptual questions are, regarding thermodynamics. Okay, so I hope all of you have at least tried to do it, or and if you have tried, just you can match your approach with me. Okay, so now first let me put the lecture numbers. So this is the lecture 3. Okay, so by the way, I want to clarify you one thing, that I am also a student. Okay, and I believe that we are here to learn. Okay, so we all have something to learn till death. So if you feel that anything is illogical uh, in these videos or in this lecture series, then you can always uh, tell that in the comment box. I will gladly accept all those things. Okay, I don't have those ego issues that I am doing M.Tech here and I have cracked GATE with AR 31, so that means I am always right. So if you feel that anything is incorrect, you must say that in the comment box. Okay, because I don't want any of you to learn the incorrect concept. So now let us proceed. So this is the lecture 3, and we will start with the Q dot G, right? So Q dot G is again, uh, I mean, again we need that 3D volumetric, 3D control volume. Okay, so let me draw the control volume here first with the axis. So these are, I am drawing my coordinate axis. Okay, so this is my x, this is my y, and this is my z. Okay, and this is the control volume having the volume v, total volume v cut, right? So what is the funda here? That is, we have a elemental small volume, that is the dv cut. Okay, and there we have the heat generation rate as q triple prime. Okay, that is the heat generation rate per unit volume, and this q triple prime is the function of which things? It is a function of this position vector of this elemental volume dv cut. Okay, and the time. Okay, nothing else. Now if q triple prime is the heat generation rate per unit volume in the elemental volume dv cut, then what will be the total heat generation rate within the volume dv cut? So that will be what? So total heat generation rate in dV cut. That will be your q triple prime into dV cut, because q triple prime is watt per meter cube, that is the heat generation rate per unit volume. Okay, so that means total heat generation rate in the control volume, I am writing in short CV, that will be equal to integral of q triple prime dV over the whole volume. Okay, that is nothing but our Qg. Okay, so now we have an expression for Qg, also we have an expression for Q dot S, and we have our basic thermal energy balance equation. So I am just going back to that thermal energy balance equation. So this was the basic thermal energy balance equation, right? So here I have the two components of this Q dot, right? One is Q dot S, another is Q dot G. Okay. So now I will put these components Q dot S and Q dot G, the expression of both, and I will write the thermal energy balance equation again. Okay. So the thermal energy balance equation becomes, okay, what? It becomes du, right, du dt is equal to Q dot S plus Q dot G. This we saw earlier. Now I will put the expression of Q dot S and Q dot G. Okay. So my equation becomes du dt is equal to Q dot G I have already, that is Q triple prime dV, integral of that, the volumetric integral. And what was the expression for Q dot S? That was this, right? So that was minus grad of, not grad, divergence of the heat flux vector Q and the volume integral over V. So I can take these two expressions under the same integral, that will be Q triple prime minus divergence of the heat flux vector, integral of that. Okay. So if that is now fine, now I have to do one more thing. So you see that this is the total internal energy, right? It is the total internal energy, and this is the total heat generation and this is the total heat generation, this one, and this is the total heat that is penetrating into the surface. So this whole equation is dealing with the total control volume, or in other words, this is the integrated form. Okay, I mean, if you do the integration on the elemental volumes dV, then you get these things. Okay, so I can say that these are my, I can say that, which color I should choose? I can say that this is my global energy balance, thermal energy balance. Okay, global thermal energy balance. Okay. Now what I want is a local thermal energy balance equation. Okay. So for that I have to define something that is an intensive property, that is small e, and small e is specific internal energy. Okay, specific internal energy. So this is basically internal energy per unit volume. Okay, just like uh, specific volume. Okay, specific enthalpy, specific entropy. So this specific what means these are per unit volume. Okay, so if this is the specific internal energy, then what will be my total internal energy U? So that will be, sorry, specific means per unit mass, right? I am very sorry. Specific internal energy means, so this thing means per unit mass. Okay, I am extremely sorry for this thing. So this is U by M. Okay, or in other words, U is integral E into dm, integral over the mass, and I can write this m as rho into dv. So this is the total internal energy of the system. Okay, now this E can be a function of what? This E can be a function of the position vector. I mean, consider the same concept here, that is I have the elemental volume dv here. Okay, so here the E, the local internal energy of this elemental volume dv will be dependent on the, obviously, the position vector and the time. Okay, so the position vector and the time. So the position vector is saying that where the elemental control volume dv is situated, and the time is saying that at which time point you are considering that. Okay, so my u is, I am writing it once more. So my u, okay, capital U is rho. Now my rho can also be a function of r comma t. E can also be a function of this thing. Okay, r comma t, because the density can vary with respect to time as well as with respect to the position vector of the control volume. I mean, throughout the system the density can vary. So if this is the system, at each and every point there can be a particular internal energy, the local, I mean the local specific internal energy, local density, everything can change with the positions as well as with the time. Okay, so that is the concept. So therefore my du dt is equal to d dt of rho, that is a function of r comma t, E, that is a function of r comma t dv. Okay, now if my material is incompressible, okay, now another thing, this specific internal energy can also be a function of temperature, as well as this rho can also be a function of temperature. Okay, now at a particular time the temperature is fixed, and therefore this rho and E is fixed. I mean, wherever you are, if you are writing the time and the position vector, now at each and every position the temperature is fixed at, I mean, and also at each time point the temperature is fixed. I mean, at a fixed time point and at a fixed position there cannot exist more than one temperature value, right? So therefore when you are specifying the position vector and the time, you don't have to specify anything else. Okay, now if we consider that this, now I am taking an assumption that my rho is a constant. Okay, so rho is neither a function of position vector nor nor a function of time. Okay, so I am considering that my rho is constant, then my u becomes, du dt becomes, I can take this rho outside of everything, so d dt of what, e, that is a function of still r comma t time dv. Okay, so now let us see, now if my, okay, so now let me introduce you something called the Leibniz theorem. Okay, okay, so Leibniz theorem. So I think you have at least studied the Leibniz theorem for a single variable, but Leibniz theorem for a dual variable, that can also be done here, and that we will be doing. Okay, so basically if you see Leibniz theorem for dual variable, so let us say this is a function, okay, fx comma y, fx comma t dx. Okay, and I have this alpha and beta as the limits, so these must be function of the time. Okay, so Leibniz theorem says that this is equal to integral, I can take the integral inside alpha comma beta, but then I have to put some correction terms. Those correction terms are d beta dt into f of beta comma t, okay, minus d alpha dt into f of alpha comma t. Okay, so now you see here I have these limits. Okay, now this is a closed integral, right? This one is a closed integral. So if I can say that my volume is not changing with time, so then effectively these bounds of integral are not changing with time. So then this can go to 0. If I apply the Leibniz theorem into this equation, so then if my these limits are not changing with time, then this is going to 0. It is going to be 0. So then this term is equal to this term. Okay, and also I am considering that my volume will not change and it is an incompressible material. Okay, so I cannot compress the material, I cannot change the density of the material. So the density is constant, the mass is also constant, that means the volume must be constant, right? So now that means this becomes du dt is equal to rho integral of de dt dv. I can also take this rho inside the control volume. Okay, I can write this thing. Okay, so now I have the expression for du dt also. So I will put this expression into this equation, okay, into this one. So just keep this one in your mind, and I will put the expression of du dt in the LHS. So integral of rho de dt dv, okay, that is equal to integral of q triple prime minus divergence of the heat flux vector, also a volume integral, okay, over the whole volume V cut. Now I can take all these things into one side and I will write rho into d dt plus divergence of heat flux vector minus q triple prime, the volumetric heat generation rate, the volume integral of this quantity, and that is equal to 0. Okay. So now can I say from this equation directly that this is equal to 0? Just pause the video for a moment and think about that and comment in the comment box. Okay. So can I say this is equal to 0? So this is, so should I put this as your homework? That is, you should find it yourself. That can I say surely that this is equal to 0 if this holds, if this equation holds? Can I say this? Okay, so let me tell it, because I think some of you at least are making your own notes in your copy. So if I don't say this, then that will break the continuity. So I must say this, right? So before saying that, I will put a small example for you. So you already know that sin x dx 0 to what? If I consider the graph of sin x, okay, this is 0, this is pi by 2, this is pi, okay, and this is y 2 pi. So 0 to 2 pi. Can I say, I mean, I know that this is 0. Then can I say that this sin x is 0? I cannot say, right? So sin x can have multiple values at all other x coordinates, and those can be anything else than 0, okay. But so this example actually shows us that integral of something, I mean the definite integral of something, if that is 0, that does not ensure that the integrand will also be 0, okay. So then under which condition we can say that this is 0, okay? Under which condition we can say that this is 0? Let me take again the example of the sin x. So first of all, why I cannot say that sin x is equal to 0 at each and every point if sin x dx 0 to 2 pi, that is equal to 0, then why I cannot say that this is equal to 0? You will directly jump and argue that we can see from the graph, right, that this value is not equal to 0, this value is not equal to 0, this value is not equal to 0, and that is the point. That is, if I change this dx, so if I take this dx here, okay, then I can say that in this dx there is no point where the sin x is 0, or in other words, if I change this integral, I mean these limits of integral, then also this value will turn to a non-zero value, okay. So the first point is, okay, if this whole thing is valid for any dv, right? So this whole thing should be valid for any dv, and the integrand Okay, so the tip has become more sensitive. Integrand should be continuous. If these two holds, if these two condition holds, then I can say that my rho d dt plus divergence of heat flux vector minus heat generation rate per unit volume, that is equal to 0, and this has a name, this theorem has a name, this is called Dubois-Reymond lemma. Okay. So I think I have written the spelling correct of Dubois and Raymond. You can check that from internet. Okay. So these subtle things actually matter a lot. Okay, in terms of the conceptual understanding. So now this is uh, what I can call the sorry, why it is not becoming a box. Okay, so this is the local balance of thermal energy. Okay, so this is essentially the differential form and this is the integral form. This was the integral form. Okay, now this is the basic equation. Now at the beginning of the derivation of this thermal energy balance, I told you that we need a governing equation for temperature. Okay, but here we are not seeing the variable temperature yet, right? So then what should we do? First of all, in most of the cases, this will be given, okay, either as a constant or you will be given a function of time and space. Okay, but these two are the functions of the temperature. Okay, this one and this one. Now let us first attack the E. Okay, the specific internal energy. Okay, now first of all, this is a thermodynamic property, right? So this is the property. Now you can define a property if the state is fixed, right? Now you can say that if there is a heat conduction, then the total body is not at the thermal equilibrium with the environment, right? But even if the whole body is not in a thermodynamic equilibrium with the environment, because it is not in thermal equilibrium, if the condition of the thermal equilibrium is broken, then we don't have to check the other two conditions of the thermodynamic equilibrium, right? So even if the total system is not in the thermodynamic equilibrium with the environment, but we assume that each and every point or the particles within the system, each and every particle, those are in the thermodynamic equilibrium, and because of this assumption only, we can define the thermodynamic state at each and every point. Thusly, we can define the temperature, the specific energy, the specific internal energy, the specific enthalpy, and all those things, the specific entropy. Okay, so we can define the properties because we assume that the each and every point is in thermodynamic equilibrium. Okay. Okay, so I should write this assumption. So each point within the system is assumed to be in thermodynamic equilibrium. Thus, we can define state, or I should write thermodynamic state actually, at each point. Okay, at each point. Okay. So now if E is a property and the substance is a simple compressible substance, actually incompressible, but I mean that is the thing. I mean, if the substance is incompressible, then also the theory of simple compressible substance, I mean, why we use this term simple compressible substance? Okay, because it is simple, because we don't care about any other effect than the uh, mechanical work, that is the PDV work. We don't take into account the magnetic and the electrical or any other effects. Okay, that is why it is a simple compressible, because we actually have to take into account the PDV work. Now that PDV work can be zero in case of an incompressible substance. Okay, so here we will consider the incompressible substance, and we can actually I mean consider a solid as an incompressible substance pretty well. Okay, so E is a function of, we can say, T and V. Okay, so then my dE becomes, okay, what, del E del T at a constant V. Okay, so this T is temperature and this small v is the specific volume. Okay, meter cube per kg, that is the inverse of the density. Okay, into dt plus del E del V at a constant temperature into dV. Okay, so now I have already mentioned that my substance is incompressible, so dV is 0. Why? Incompressible. Okay, fine. Next, so then this term actually is not there anymore, it is 0. Then I have this one, right? So what is this? So now let me introduce you the concept of the specific heat, CV. So this is specific heat at constant volume, okay, of a gas. Okay, so the by definition this is the heat required per unit mass, okay, per unit change of temperature. Okay, I mean this is the heat required per unit mass to rise the temperature of that mass by 1 degree. Okay, so this is the definition of the CV. Okay, so by first law of thermodynamics, for a simple compressible substance, this Q, if I am giving some heat into the system, so that can introduce some change in internal energy, right, plus some work done. Now if my work done is 0 because there is no displacement work, no displacement work because my volume is 0, okay, and that is because change in volume is 0, or I should write dV is 0, okay. So that means this Q is equal to del U. So this is equal to del U by M T, right? Okay. And okay, so specific, okay, if I mean because of this specific word only this mass has arrived. If, and actually the total word is specific heat capacity, okay. These terminologies are also very important. That is why I am giving a very great emphasis onto these things. So now, had I been told only heat capacity, then this M in the denominator should not be there. So only heat capacity is what? The heat required to rise the temperature of a particular body by 1 degree. So that is Q by delta T. Okay. So now this is equal to what? Now I can write this U by del U by M, okay, by delta T, okay. So this is nothing but del E by del T, okay. So the definition is actually limit delta T tends to 0 del E del T, okay, and that is nothing but dE dt. I can also write this as del E del T at constant volume, okay. And now you will see that Cp and Cv, okay. Now Cp is what? Cp is actually the same thing, the del Q, okay, I mean the Q by M delta T, but at constant pressure. So pressure is equal to constant, okay. Now if the pressure is constant, okay, so then my Q is equal to U plus what? P delta V. So P, I should write delta V here. So this is del U, okay. So del U, right, or I can write, so let me put this here afresh, okay. So my Q is equal to U2 minus U1 plus P into V2 minus V1, okay. Now I can write this as U plus P2 V2 minus U plus P1 V1, okay, I mean U1 plus. Now this P1 and P2 are same, so that is why. And why they are same? Because it is a constant pressure, because this is a P equal to constant process, isobaric process, right. So then this is equal to new property, that is H2 minus this is equal to H1, this H2 is H1, and this is called the enthalpy, okay. So for constant pressure process this Q becomes delta H, right. Now you see that if my material is incompressible, then my change in volume is 0. So writing H2 minus H1 is as good as writing U2 minus U1, right? These are same. Okay. And why these are same? Because here if you write H2 minus H1, then you can directly go back to this step, then you can directly go back to this step, and here this V2 minus V1 is 0. So for incompressible, okay, substance, del H is equal to del U, okay, and that means Cp is equal to, okay, again, so by this time you should already see that this Cp should be what, del H del T, okay, at constant pressure obviously, and that is equal, or I can write this as, okay, it is okay, and now this should equal to Cv, okay, because be it a constant pressure, I mean even if it is a constant pressure process, but this del H I can write as del E because of this thing. So if del H, del of capital H is equal to del of capital U, then I can write dividing by M, this is equal to del of U by M, that means del of small h is equal to del of E, okay. Because of that only I can write this. So for my incompressible substance, especially for a solid, okay, and also for a liquid, I have my Cp is equal to Cv is equal to C, okay. So basically this Cp and Cv, this concept are practically valid for a, I mean for gases. Theoretically it is valid for a solid, liquid and fluid, okay, I mean solid, liquid and gas, but practically because solids and liquids are almost incompressible, okay, that is why the concept of Cp and Cv separately, they are only valid for gases, okay. So now, but here for the sake of generality we will consider this to be, okay, this to be Cv only, okay. So my dE is Cv dt, okay. So one of my job is done, because now I can write this dE dt is equal to Cv dt, okay. So one of my jobs are done, that is to express this E in terms of temperature, E as a function of temperature. So now my equation becomes what? So thermal energy balance becomes what? Rho Cv dt, right? I think I am correct, yes, because Cv dt is plus divergence of heat flux vector minus q triple prime is equal to 0, correct? So now you see that I have already told that this thing is given, okay. This part I am done, only this part is remaining, okay. Now I have to write this as a function of temperature. This is my second task, and that will be done by the famous Fourier's law of heat conduction, right? So I think that I will start in the next lecture. Now you guys might be thinking that why in the next lecture, because Fourier's law is just a law and it can be stated within a sentence, right? That is correct. That can be stated within a sentence. But the so-called famous mathematical formulation of the Fourier's law, that is Q is equal to minus Ka dt dx or dt dy, okay, where the K is a numerical constant, okay. If not a numerical constant, it can be a obviously a function of the temperature, but it is a single value, okay. So that is actually not true, or if that is true, there is there is an assumption behind that equation, and the assumption is that the material is isotropic, okay. So basically I want to prove that thing from the scratch, okay. That is why I will dedicate almost 1.5 lecture on the Fourier's law of heat conduction, because to prove that I need the help of the tensor algebra, okay. So first I will teach some tensor algebra that will be needed for that, and then I will do that. Now if some of you are thinking that I will only prepare for the college semester examination, or I will only prepare for the GATE and ESC, then my friend, you can skip the next lecture, okay. But let me tell you that the application of the tensor calculus, that is not limited to only this thing. The tensor calculus has the application in almost each and every area of mechanical engineering, be it fluid mechanics, be it solid mechanics, be it heat transfer, and anything, okay. So all the core subjects, they have the application of the tensor calculus, okay. So even if you are in your B.Tech, I always suggest that you should study the derivation of all the equations, be it Navier-Stokes, be it heat conduction or anything. You should learn it from scratch. You should go through the derivation. So I am not telling you that you should be fluent while deriving the Navier-Stokes equation, but at least once in your life go through the full derivation of the Navier-Stokes equation. And by when I am telling that you should go through the full derivation, not just by seeing a lecture or just by seeing the pages of a book, but understand each and every step by heart, okay. And if you have to go through the proof of the uh, equation of the fluid friction, that is the constitutive law, okay, relating the stress and the velocity, okay, that is the famous law of the Newton's law of viscosity, right? So Newton's law of viscosity, what you have already studied, that is tau is equal to mu du dy or mu del u del y, anything, okay. That is not the actual law. The actual law has come from the Stokes law of viscosity, and that is not mathematically that much simple, okay. But you should learn the derivation of that thing also. And now the mathematical derivation of that can be done in so many ways, but the simplest way is by the application of tensor calculus, okay. Obviously that is also a constitutive law, and there is also an assumption, that is the material is isotropic, the material is homogeneous, and there is a linear relationship. All these assumptions are there, but then also to derive that from a scratch, you should know the tensor calculus. Okay, so you cannot beat that. Yes, if you are a student that, I mean, if you want to just crack gate and if you want to secure your life by getting a job in a PSU, then I think you don't require all these things. But by any chance, if you are someone who wants to join higher studies, then you will need tensor calculus. You cannot go away, or you cannot avoid the tensor calculus and the tensor algebra. Okay, so uh, enough of lecture. Now in the next lecture I will start from here. Okay, the Fourier's law of heat conduction. In the first part of the lecture I will teach the tensor algebra and how to deal with the index notation. Okay, then I will say that why only for isotropic materials K is a single valued constant. Okay, so until then, goodbye.